This is my 2-channel receiver. 2 oscillators here, and a PLL system, and then hybrids and Schottky mixers, giving I and Q going to a sound card in a computer, and the same for the 2nd channel. And the signal goes into this hybrid, and what comes before is different from time to time. Now I have discovered a problem with this system, and that is correlated noise at very close range. 10 Hz offset or below that, or maybe all the way up to 20 Hz. I cannot say for sure. One explanation could be pulling between the oscillators. It means the signal from one oscillator would go here and leak somehow and come back into the other oscillator. To check for that, I have changed here. The oscillator is a selective amplifier with positive feedback through the wire that I have now broken. There is a dummy load on the input, and I'm looking at the limited output with the spectrum analyzer. And here is what I see. The level of the lowest of the 2 frequencies is marker minus 91 dBm. Yeah, also here. Minus 92 perhaps. The normal level when running the oscillator is about plus 10 or maybe plus 13 dBm. It means that the leakage from the other oscillator is about 100 dB below the desired signal. As you can see, there are 2 peaks. One is the leakage from the device under test. I switch off that. And there are capacitors, but now there is only the local oscillator, the one that I wanted to not have, at minus 92 dBm. I put the cursor on the wrong signal before. Well, sometimes easy mistakes. Anyway, I want to reduce this. I have disconnected the output here, and that didn't make any difference. The oscillators are sensitive to mechanical vibration, so they are standing on plastic foam, and this is a heavy piece of iron, several kilograms, but they are standing pretty close to each other, only a couple of millimeters. So I moved them apart to some extent. They are still well isolated from mechanical vibrations. And this made a difference, about 10 dB. I have placed the oscillators on some bent aluminium sheets like this, and placed these some distance apart. And now the leakage is better than minus 170, probably more like 120. This peak is not far above the internal noise of the spectrum analyzer. Now I have put back the cable from the coupler into the local oscillator. And I am still looking at the amplitude limited output, and now the level is minus 100 here. So there is a signal coming through that cable. I have disconnected here again, and now I look with the spectrum analyzer at what comes out from this coupler. And the level here is minus 85 dBm. I have now increased these two attenuators from 20 decibels to 26 decibels. Means 12 dB more attenuation going this way around. After that, the level I see at this point where I was looking previously is about the same for the signal leaking this way and for the signal leaking that way. And I don't want to attenuate here, and I don't want to introduce amplifiers because the power is pretty high. And I want to avoid adding noise also. Now I have again connected the spectrum analyzer to the limited output of this selective filter amplifier, where I had minus 92 dBm originally. And now I see minus 150. That's a more than 20 dB improvement. And now I am looking at the limited output of the other amplifier filter, and it is even lower. It's minus 120. I have now switched on the test signal, and the frequency of the LO is here and the test signal is there. So something is saturating, and that has to be the Schottky mixers. So I reduce the, first I look at the amplitude, minus 82. And now I reduce the level of the test signal by 5 dB. And now things look much nicer. I'm looking still at the limited output of the of one of the oscillators, and I see mainly the signal from the device under test, and that is 700 Hz away, so it should be harmless. And here is the limited output of the other oscillator when it is not running as an oscillator. Also here I have an ugly spectrum when bringing up the signal level by those 5 dB that I was always using until now. I have increased the sound card gain to compensate for those 5 dB of attenuation. Means I have lost some little amount of dynamic range on the receivers. And now I will have to wait for quite some time before I know whether this helped or not, whether I have negative values on the real part here. Here is what I see now. This is after 16 hours. And I can compare this to what I saw in the previous video, nerds58. And I have it here in the same scale. You can see if I move it. That the x-axis is the same. And the important thing here is the blue that was going down and reached minus 150 at this point. Now it reaches 150 here, about half the frequency. So things have improved. If I try to read the value at about 5 Hz, I see minus 130. in the old measurement, but here I see minus 130 at a closer range. So there is still far too much correlation between the two channels, but the limit where I can get a reasonable result is a little bit lower. And of course I don't know whether the problem is still caused by crosstalk between the oscillators with frequency pooling as a consequence. Things may change because impedance changes when both signals reach the mixers, and I cannot evaluate the coupling between them when both are running, because the frequencies are very close or the same when they are locked. Anyway, I can estimate the value for the sideband noise now, the phase noise, at 10 Hz. To do that, I expand here. This is a new function that I can do, these expansions. Let's say 20. And then I move it vertically. Let's say I put here 100. And now I can estimate some things. The negative real part goes like this, and the imaginary part follows a very similar pattern. So I can extrapolate the negative part downwards, and I can say that at this point, where it goes from negative to positive, or rather at this point where there is a minimum, the negative part and the positive part are equal. And if I extrapolate here, I find that this is the value that I should assume to have at, is it 6.5 Hertz. Going from the other side, at 15 Hertz, I have a good separation between the real part and the imaginary part, so I can trust the value here. At 10 Hertz, this separation is much smaller, so I have a contribution from random noise here, and I have a contribution from the negative part with the opposite sign also. So, taking these two things into account, I would guess that at 10 Hertz the noise is minus 145, means half a dB below where the curve is now. And that should be accurate within better than 2 dB, probably better than 1 dB. So 145 at 10 Hertz for the Wenzel, and something is not good with my system. I cannot go to lower offsets. This is the loop filter I've been using for the PLL up to now. I have made it significantly slower by adding 4700 microfarads in parallel with this one, making it 3 times bigger. And here I have added 220 microfarads to make this capacitor 10 times bigger. The resistor at the slowest setting is 1.8 kilo ohms here and 100 kilo ohms here. So the corner frequency is down by a significant amount now. This is a factor of 11, or here is a factor of 3. And I haven't really made any computation, but I should see it looking at the evaluation of the correlation spectrum. And here is what it looks like. I would like to get a value at 10 Hertz that's here at this point, and it is a bit uncertain still. What I had before, I have that saved, so I click on the here. So the correlated noise that comes with the negative sign is here with the old filter, and it is a little bit weaker at 10 Hz. Maybe at 10 Hz. Something like 10 or 15 decibels weaker. I think still some other mechanism is responsible for most of this correlation with negative sign. So I will do some experiments to see if I can find a solution to that. But I can extrapolate this curve and get a reading at something like -147 or -146 or so at 10 Hz. And that is really very good. I will save this curve with different scales to get readings for the Wenzel oscillator, because now it has been running for 37 hours. So it has very good statistics. You can see the curve is almost flat. In the previous measurement, I had restored 20 decibels in these attenuators. But I had fixed a problem in one of these amplifiers because it was oscillating at about 500 megahertz. So a 1 PF capacitor at an appropriate place in both of these removed that and increased the gain in one of them significantly. So the loop gain has been a little bit bigger in the previous experiment. Now I have changed again and replaced these to 30 decibels. With 30 dB here instead of 20, I have less feedback this way for a reduced pulling. It should be even lower than before when I had 26. But there is another thing. Adding 10 dB here and here reduces the level out from the mixer by not quite, but almost 20 dB. So the loop gain in the PLL loop is now about 18 dB lower, which means that the addition of phase modulation through the PLL into the frequency control, here, this signal is 18 dB weaker, so there should be much less low-frequency noise introduced from the loop. And of course also that lower pulling between the oscillators. The remaining pulling should be from this way. And I don't want to do anything about how to reduce coupling through these Schottky mixers. We will see what is the result of this. It will take many hours. Now it is 39.5 hours later. I can see there are some new problems with my setup. The trace out here is not as flat as it should be, and the imaginary part is very strong here. That's some kind of spurs. And here is a clear problem, a spur that comes negative on the real part. I can compare this with what I had before, which I have saved. It looks like this, and it's very different in that the imaginary part is down here, as it should be. Now, I'm primarily interested in the close range. This is the old result, and here is what I got now. And it is very similar. The size of the imaginary part on the old curve and the new curve, they are comparable in this range here. But something is wrong, and I will try to find it. And the easiest way is probably to look for this peak, which will be visible already at a much shorter time. I don't know quite yet how much shorter, but I will find out. Anyway, first I will try to evaluate the noise at 10 Hertz from this measurement and compare with the previous one. I have put some mark on the screen. This is the old measurement, and I can move the camera, and here you can see I am on top of the curve, and here I am looking from the bottom. So keeping the camera here, and now I switch to the new measurement. You can see it is very much on the same spot. The arrow here is a mark for, and I can't really measure. From this curve I would guess minus 147. And from the old curve, the same. So that is as far as I can come now. With this arrow at 10 Hertz. I will have a look for the source of this problem, and also I can see here the non-flat curve. Something has gone wrong. With these settings I can see the problem fairly well already after 1 minute. You can see here the negative peak in the real part of the correlation average. But more importantly, in channel 1 I have a strong signal here that is visible without any correlation. And it is present also in channel 2, but very weak. That's why it doesn't come higher than that. So somehow something leaks into channel 1. That should be possible to find out. I have swapped the two oscillators, making a wire from this LO to this coupler and from this LO up to this coupler. And now the problem is clearly in channel 2 and not in channel 1 as before. The phase angle has shifted also. It comes positive in the real part, but very strong in the imaginary part here, and also strong in the direct signal here in channel 2. So something is wrong. I get phase modulation into channel 2, and now that one is the one which has the PLL input on it. And the PLL circuitry is here. Before it was sitting with a very good ground connection on the system here, on the ground metal sheet that is everywhere here. And also now I have an oscilloscope connected. So I will clean this up and see if things get better. With 44 hours time to collect correlation averages, I have 287,000 averages. The square root is about 500, and the decibel value for that, the logarithm, gives me 27 decibels. So the correlation advantage is 27 dB now. It is this much from here to here, 27 dB. There is a parallax problem because the screen is fairly far behind the glass that is in front of it. Anyway, at this point here, where my receiver is at minus 1 45. 27 dB is overkill. The noise is about 15 decibels below the signal, which is the noise from the device I'm testing. Therefore, I have a flat and nice curve. But here it starts to look noisy. And that is because of the sideband noise that grows rapidly because of my poor local oscillators, 700 Hz below 10 MHz. So when I'm looking at 10 Hz, that's here, I have to go to this point, and then I find that the signal is, well, 9 dB or so above the noise. The imaginary part looks fairly strong. Maybe there is a spur here. But the uncertainty of this curve is in the order of 1 dB or a little bit more. And to get a more accurate result means to know whether it is a spur or whether it's just random. I will have to wait a couple of more days. But I have this information saved now, because there is always a risk that the computer will crash. Windows might want to install something, although I tried to tell it not to do so. Or there could be a power out of the mains or something. Running for several days is not always reliable. I can compare the screen I have now with the screen I had before making those changes to the hardware. Here is the present result, and here is the previous one, from which I concluded that at 10 Hz the noise is at -147. Now it looks more like it is at -145, but the value here is a bit uncertain, only 4 dB above the imaginary part. Bad luck, the computer crashed, I got a black screen and everything completely dead, and I had to restart the computer. The screen was also switched off. So now I have 64 averages and I'm running with the UADC4. I have started a second instance of Linrod, which I can select here. And this is with a Delta 44. And as you can see, it is very similar. Because the noise is dominated by the noise here, which is the phase noise of the local oscillators of my hardware. So I go back to the Delta 44 here, and it's fairly similar. If I go out here with the Delta 44, and here is the UADC4, look at the noise floor. It is significantly lower, and this is already at about 50 Hz, so the difference is bigger at bigger frequency separations. But I'm interested in the 10 Hz. What is the noise at this close range? And I have to wait quite some time before I get a reasonable reading. At this moment, the average is negative, but it is noise, because I'm only a little bit below the channel values, and therefore noise can dominate at some frequencies, and I go for the other sound card. and it looks very similar. As it should, because the noise is dominated by noise from the hardware. Now I have collected correlation spectra for a little more than 3.5 hours. That's 24,000 spectra almost. At 10 Hertz, 10 Hertz here, I see minus 145, but judging from the curve, the uncertainty is something like plus minus 3 decibels. This is the UADC4. And now I switch to the Delta 44 instead. And as it happens, it also shows minus 145 at 10 Hertz. But at 15 Hertz here, I have a much lower reading because there are negative components, and that has to be noise. The signal to noise ratio degrades the further out I come. I have now collected correlation spectra for 110 hours, and I will stop here. First I can show this is the result for the UADC4 sound card, and I can switch to the Delta 44 now. And as you can see, it is very similar but much more noisy at the wide separation here of 250 Hertz. But if I go to the close range here, this is still the Delta 44. And here is the UADC4. At close range they are very similar. I will place these graphs on paper and do a more careful evaluation from paper. Here is the phase noise from the UADC4 card on paper. I can see here that 10 decibels from 140 to 150 is, oh, there's the light, 43.55 millimeters. And then I can check the distance from the curve to the dB line and compute what are the noise values, and I get it with 1 decimal, actually 2 decimals, but the curve is not accurate as that. So I get these values for the UADC4, and similarly I get values for the Delta 44. This is the same measurement, and I should expect the same results at close range, where the noise of the local oscillators is the dominant noise source. These two measurements differ only in the noise that comes from the sound card. The imaginary part is just single pixels. They are very hard to see. I have to make them 3 by 3 pixels for the future. I will fill in and make a curve of the imaginary part. And there is also the direct measurement. You can see here some dots. I will fill in those to make them more visible. With an average of 721,000 correlation spectra, the advantage is the square root of this, which is 849, and converted to decibels, 29.3 dB. And on this image, that means 65.3 millimeters. The upper red trace here is the mean value of the 2 channel average power spectra. And the second red line here is 29.3 decibels below that. That's the noise level for the correlation, the average correlation spectrum. This noisy curve here is the imaginary part, and here is obviously a spur. And we can see it also in the real part. And then here, this looks very much like noise. It can be maybe up to 5 dB above the average noise level, but it can also be very close to zero, like here. And the signal to noise ratio is the ratio between the real part here and this correlation advantage curve. And it's 12 decibels as worst, and at the other end, at 40 Hertz, it is 18 decibels. With the delta 44, the result is very similar. Here at the highest end, at 40 Hertz, it's 15.8 signal-to-noise ratio, while the UADC4 was 3 decibels better. But at 10 Hertz, the result is the same for the signal-to-noise ratio. And the curve generally looks very similar. So the different sound cards do the same as expected. Here is the curve from the UADC4 from 50 Hertz up to 250 Hertz. The signal-to-noise ratio is 22 decibels here, and not very different at the 50 Hertz limit. It's like you saw in the previous picture at 40 Hertz, roughly. So the reading should be very accurate with respect to statistical errors. And indeed, the curve I see here, the measured, is very flat. And that is, of course, the phase noise of the device under test. But here is the result with the delta 44, and it looks a little bit different. The measured result is a bit noisy, and typical uncertainty is plus minus 1.3 dB. And that is at a signal-to-noise ratio of 11.8 dB. That's from here to here. So the measurement I made at 10 Hertz had a similar signal-to-noise ratio, so the error is probably less than 1 dB, but it could be up to a little bit more than that. And it was at 110 hours, 4.5 days, and making a better result is beyond what I'm interested in spending time on. Here at about 240 Hertz, there is some artifact. It has to be a spur. It is strong in the imaginary part, significantly above the noise level, and it looks like there is generally a noise problem in the imaginary part out here, while at lower frequencies the noise behaves as expected. So something is not quite as one would like it to be in the delta 44. But I will evaluate the levels of the sideband noise using the UADC4, which is obviously a good measurement because all the way things look nice. With an expanded vertical scale, I can read the decibel values easily with 1 decimal or even with 2 or 3 decimals, although the accuracy of the curve isn't good enough for that. And I don't go higher than 200 Hz because the curve starts to bend downwards a little above that, and that's because of the frequency response of my system. This is a setup for close range only. Now I have what I think is accurate information on the phase noise of the Wenzel oscillator. The results compare very well with the typical performance according to the data sheet. What I see is 4.2 or 5 decibels better at the specified frequencies 10 and 100 Hz. This is a recent paper on ultra-low phase noise oscillators for 10 MHz. It's from January 2019. And this is where you can find it. Figure 20 shows the performance of one of these oscillators. Here I have this figure magnified on paper. Note the gray area here, coming very close to the point of measurement at 10 Hz. The curve is noisy, so I made my own guesses. You can see the red line on where to read the noise at the frequencies where I also measured the Wenzel oscillator. So it looks like this, my guesses. And on the more expanded scale, it looks like this. And I have filled in the border between the gray area and the non-gray area, and it is not visible within this cursor area. I find 147.6 at the center of the cross, 148.54, while the specification here says minus 148.6. So that's close enough. Here is a graph of the results of these measurements I made in this video. I will use in the next Nerds video to study my selective amplifier and oscillator. The amplitude noise is much lower. You can see here the dB scale of this diagram. The upper blue trace here at about minus 158 dBc per Hertz, that is the average power from the 2 channels. The lower blow trace here is when I add those 29.3 decibels of the correlation advantage from the 721,000 averages. So I have a signal to noise ratio of 18 dB. Here is the noise signal, the real part of the correlation average. And it comes at about minus 169 dBc per Hertz, and it's fairly flat until about 100 Hertz when it starts to go up a little. And at close range it goes up to, well, is it 155 or something? More about that later. One thing is these peaks are red, means they have the opposite sign. This is at 50 Hertz and 100 Hertz, also red. But note that there is also the black, which I have written here and here. That's the imaginary part. What I have down here, it goes up all the way. It means that this signal is equally strong in the real part with negative sign as it is in the imaginary part. where I don't know the sign of it. So the modulation on 50 Hz and 100 Hz and the other overtones is in 45 degrees between the two channels. But I have also a peak here, and this is black, and it is weak in the imaginary part. And here is another one, it's also black, and it's weak in the imaginary part. They belong to the sound card, and they are in phase in the two channels. And I don't know exactly what they are. This is all with the UADC4 sound card. With the Delta 44, it's quite different. Remember these numbers, 169, 158. Here I have 145 and minus 153. There is a strong amplitude noise modulation over the whole frequency range. The signal to noise ratio is very good. It's 22 dB. So this is a real noise signal in phase between the channels. So it is from the sound card. The two channels have a common voltage reference which is noisy and adds noise in the two channels. So this is useless. I evaluate the close range amplitude noise from this graph, and at 70 and 100 Hz from the previous one. And here I get a lot of numbers, and it's what it looked like on the diagram. The AM noise is about 10 decibels below the phase noise in the range 10 to 100 Hz. I cannot be quite sure that this is correct. The UADC4 uses a single chip to convert both channels. Presumably they use the same voltage reference. It seems to be much better than the one used in the Delta 44 card, where there are two ADC converters, but they have the same external voltage reference. So anyway, AM noise is much lower, and I know now what I have with my setup, and I can look for changes in the AM noise as well as changes in the phase noise when the signal passes through crystal filters and amplifiers.